long, thin rod as shown. If each of the three rotor helicopter blades is 3.75 meters long and has a mass of 160 kilograms, calculate the moment of inertia of the three rotor blades about the axis of rotation, and B, how much torque must the motor apply to bring the blades up to a speed of 5 revolutions per second in 8 seconds. So for part A, they simply want you to calculate the moment of inertia. So in order to do that, you should reference the different geometries on page 208, and you'll find that the moment of inertia for a single rod rotated about its end is equal to 1/3 the mass of the rod times the square of its length. In this case, the total moment of inertia of the array, the entire rotors together, is the sum of blade number 1 plus blade number 2 and plus blade number 3. Since they're all identical and we have all of the symmetry here, we can basically just say, all right, well, it's 3 times the moment of inertia of one of these things, or 3 times 1/3 ml squared. So we see then that the 3 and the 1/3 cancel out, and I'm basically left with the total moment of inertia for all of those rotors together is equal to the mass of the blades times the length squared. And the mass is 160 kilograms. And I'm going to multiply it by the length squared, which is 3.75 meters. And I have to remember to square that. Okay, so that's part A. The answer then is 230 kilograms meters squared are the units for the moment of inertia. So the answer to part A is 230 kilograms meters squared. So then, the question goes on to ask, then what is the necessary torque required in order to bring the blades up to a certain speed, and they give that to you as 5 revolutions per second, and they give you the time of 8 seconds. So we've got some kinematics working up in here. They want to know the torque. We're ignoring any frictional torques here, so the only torque that's going to be applied is the torque applied by the engine of this helicopter. So it is the net torque. We're given a final angular velocity. It's equal to 5 revolutions per second. We know that we start from rest, so therefore our initial angular velocity is equal to 0. And we know that the time is equal to 8 seconds. We could immediately see here that we could use the second equation to find the angular acceleration. And once we know the angular acceleration, we could basically say, all right, well, using Newton's second law, torque is equal to I alpha. I know the moment of inertia here from having completed part A of the problem, and the angular acceleration can be found from doing some kinematics. I should also recognize that this is not given to me in standard units of radians per second. It's given in revolutions per second, so each revolution is 2 pi radians, so I'll have to deal with that. Once I convert the 5 revolutions per second, I get 31.4 radians per second. And then I'm ready to proceed and solve for alpha here using the second equation of kinematics. Omega final is equal to my initial angular velocity plus my angular acceleration times time. Solving for angular acceleration, I get omega final minus omega initial divided by time is equal to my angular acceleration. And now I'm going to get 31.4 radians per second minus 0 divided by my 8 seconds is equal to the angular acceleration in the system. And I get 3.93 radians per second squared when I run that through my calculator. And now I'm ready to proceed with this kind of last piece, which I'll do over here, of solving for the torque necessary to be applied to the rotors. So the torque's going to be my moment of inertia, 230. Let's not forget the units, kilogram meters squared. And I'm going to end up multiplying that by the angular acceleration that I just figured out, 3.93 radians per second per second. And so therefore, the torque that I get is going to be equal to 903 Newton meters. And if I wanted to, I could kind of just simplify that to, or truncate it for numerical significance to 900 with 2 sig figs.